Welcome back, everyone, to the eCore Academy e-learning platform today. My name is AJ Raj, back with yet another geometry video for you all. Of course, today's lesson topic is volumes of pyramids. So we're going to be moving in, of course, into more specific shapes. And of course, we'll be looking at more complex relationships. This is heavily correlated to our cones and our cylinders topics. We're going to be moving into our three-dimensional topics a bit more as we go along. With that being said, before we jump into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications by hitting that bell icon right next to the subscribe button. So the whole theme and purpose of today's lesson is to discover what are some properties of pyramids and what are their volume formulas. So we're going to be looking at dissecting what pyramids are, and of course looking hyper focus at their volume formulas. And of course I'll also be including surface area, which is basically one of the basic properties of pyramids. Pyramids, of course, in real life are actually very interesting. If you don't know already, if you've ever heard of the pyramids of Giza in Egypt, those very pyramids are one of the largest historical structures to be built at such a time, at such a complexity. It's quite interesting and basically a worldwide marvel. They made those for each and every one of their Egyptian pharaohs who had passed away, and they would bury them. They would have their tomb inside the actual pyramid, and they were absolutely massive and amazing to have been made with such materials at such an ancient time, with the lack of modernized technology that we have today. So pyramids, very, very smart structures. Structurally, pyramids are very popular because they're actually one of the most durable type of structures. So if you're looking at a building, you would want a pyramid type building because it can withstand any wind or as such, because it's going from a sturdy foundational base to a smaller and smaller levels going upwards. So give you a little bit of a spiel. Now let's jump into the actual content of today's lesson. So let's look at the parts of a pyramid, part one. So I'll split this into three different parts for the parts of a pyramid. So let's look at the vertex of a pyramid. I'm going to be dissecting the different parts of a pyramid, and then we're going to be utilizing these parts to develop our volume formula, and then later on our surface area formula as well. So a polygonal or pyramid is a three-dimensional figure with one base that is a polygon, and all other faces, called lateral faces, are triangles that meet at a single vertex. So a pyramid, if you imagine that, it's any sort of figure that's on the bottom, any sort of polygon that's on the bottom. That's why I said polygonal pyramid. You can have any sort of polygon with any straight edges, and basically what it does is it takes those edges and it basically connects them to one singular point. So you'll have a bunch of triangles formed by connecting all of the different vertices together, and they meet at a singular vertex. That's basically an overall definition of pyramid. You should already be familiar with what a pyramid is coming into geometry, but of course we need to get you all acquainted with the actual geometric term and definition of pyramids under the laws of geometry. And then of course you have your vertex of a pyramid. As I mentioned in the definition of a pyramid, it's the common vertex at which the triangular faces meet. So you have your base, which is any polygonal shape, and then afterwards you're going to have these lines that connect all of these vertices of that polygonal base, and they're all going to meet at a singular vertex. And all of these faces that are made are going to be triangular faces, and those triangular faces will meet at one common vertex, and it's going to be at the peak of the pyramid, and it's going to be one singular point where all of them meet. And so this is a pyramid, just as an example. As you can see here, this bottom part is a square here. Just label that out for you. So that's a square. And then all these faces, so there's four faces, and that's equivalent to the amount of sides that your actual base has. And all of these sides are going to be triangles. And all these triangles are connecting all of these separate vertices of this square, and they're going to be meeting at one common point. All these lateral faces, they're called lateral faces. These triangles are called lateral faces, or exterior faces. Faces that are seen basically on the outside. Because most of the time your base is going to be hidden. And oftentimes if you have a pyramid, it's not going to be bouncing off of its vertex. It's going to be planted off of its base, so you won't really see the base. But we have a diagram set up here, and this is your vertex. So it's the top part where all of these triangles peak up and form a singular point. Moving on to parts of a pyramid, part 2. Let's look at base edges and classification. So we're moving on from the actual vertex of a pyramid, and of course the basic definition of a pyramid as well. We're going to be moving on to base edges and classifications of pyramids, how we're actually going to identify them and name them to keep that separate and uniquity with each and every one that we're given. So the pyramid is classified by the shape of its base. So like I said, the base is basically the bottom part, the balance point where it's actually placed or planted onto a surface. And the pyramid is classified by the shape of its base. And the bottom of the pyramid is not a lateral face, and that's of course your base. So it's the base is the side that is not a lateral face. So all sides of a pyramid are going to be lateral faces, except for the base or the bottom part. And lateral faces are any of those triangles connecting at the vertex, of course, connecting the vertices of your base and forming that vertex at the top common point of intersection. And a base edge is one of the edges of a base of a prism or a pyramid. So basically any of the edges of that actual base. They're also going to be parts of your lateral faces, and they originate from your base. So if we're looking at this square pyramid, it's going to be a square pyramid because this base is a square. So that means that this is going to be classified as a square. Oops. So this is going to be classified as a square pyramid. And that is because its identification, the base is going to be a square. So that's the base is a square. And of course, all the lateral faces, I'll say lateral face here. And that's going to be all around this pyramid on all 4 sides. And like I said, the amount of lateral faces that you're going to be given on your pyramid is dependent on the number of sides that your base actually has. So those are all your lateral faces, and they're always going to be triangles. And in this case, it's going to be an isosceles triangle as shown. And they're all going to be of equivalent length if you have a regular polygon. If not, they're going to be of different lengths, of course. But with regular polygons that have all equivalent sides, equal angular polygons, equilateral polygons, I apologize. Equilateral polygons, such as equilateral triangles, squares, then you have your pentagons, hexagons, all that sweet stuff. They all have equivalent lateral faces, which are your triangles of your pyramid. And of course, your base edge is one of your edges of your given base here. And this is one of them. This is another one. You have 4 here in this instance. And that judges the amount of lateral faces that you have. And of course, this base edge is also going to be shared by the lateral face as shown here. Now for parts of a pyramid, part 3, let's look at lateral edges and regular pyramids. So lateral edges are an edge of a polyhedron, which is of course another classification for a pyramid, and it states that that a lateral edge is an edge of a polyhedron that is not a base edge. So it's basically any of the edges that are not shared by the base and are only separate to all of the lateral edges, lateral faces. And a regular pyramid is basically a pyramid. It's a type of pyramid. Classification is a pyramid with a base that is a regular polygon, meaning a regular polygon which has such as, well, in this case, we're going to be looking at specifically equilateral polygons. So I'll state that as equilateral. Basically, I want to say figures with equivalent degree measures and equivalent side lengths. And their lateral faces are going to be congruent isosceles triangles. Like I said before, because you have a regular base, all lateral faces are going to be equivalent, which are your isosceles triangles. And if we're looking at this pyramid right here, if you look at a lateral edge is any of the edges on this pyramid that are not shared by the base and are only separate to any of the lateral faces. So like I said here, this is a base edge because it's shared amongst. So this is base edge. And this would be one of your lateral edges, and of course you're going to have 4. And that's also determined by the number of base edges that you have is going to be equivalent to the number of lateral edges. This is your lateral edge. And it's separate only to the lateral face. Think about the root lateral It's separate to the lateral face, and it's what basically arcs up and intersects at your vertex and creates your triangles, your isosceles triangles. Now let's move on to the volume of a pyramid, what we actually came here for to dissect, and then we're going to use the volume pyramid, look at some of its relationships and the net of a pyramid to actually determine the surface area, because volume and surface area, they go hand in hand when looking at three-dimensional figures in turn. So let's look at the altitude and volume formula. And altitude, if you don't already know, is of course a determining factor for any three-dimensional figure in order to discover its volume. But specifically, the altitude of a pyramid is a perpendicular line that joins the vertex to the plane of the base. And it lies in, on, or outside based on the type of pyramid it is. And it also is equivalent height. So let's break this down here. The altitude of a pyramid is basically, if you look at triangles in turn, I'll just give this diagram here. If you look at this pyramid here, if you're taking your vertex here, you're just going to draw a straight line down in such a manner that it intersects your base. Sorry about that. In such a manner that it'll intersect your base plane, which is basically that two-dimensional outlook, at a 90-degree angle in some manner. And this plane is basically the two-dimensional. It's basically your base. It intersects your base at a 90-degree angle, and is going straight down if it's a regular polygon. If it's a regular pyramid, like I said, a regular pyramid is anything that's an equilateral and equal angular base. But if it's not a regular pyramid, then it's going to be an oblique pyramid. And an oblique pyramid is basically a pyramid that does not have a regular base. It'll have a base such as like a rectangle. And basically what happens is your vertex, it's not going to be directly above your base. It's going to be on a slantwards. And your altitude can still be calculated that way. But it's just not, it's going to be off, and your slant heights will be different. And I'll explain what that means there. And it can lie in, on, or outside based on what type of pyramid it is. So if it's a regular pyramid, it's always going to be in. But if it's an oblique pyramid, it can either be on or outside depending on how drastic of a vertex or drastic of a difference that your base is. So you could have a vertex that's way outside, but it can still touch the plane on the exterior of your given pyramid. So now let's look at the volume of a pyramid. Let's look at the equation. So the equation is 1/3 base times height. So B equals base and H equals height. Now, how do you get this formula? So just like a triangle, if you look at a triangle is technically considered half of a rectangle. So that's why it's 1/2 times base times height. But in this instance, it's not necessarily that case. Height is referring to your altitude, which is basically your three-dimensional outlook. So you're multiplying your whole base area by your height. So it's a bit different here. It's a whole base area of the base times the actual height divided by 1/3. Now, the reason that's the case is actually very interesting here. If you're looking at this pyramid here, the square pyramid here, you have a square base here. Now, what if we took away this 1/3 here? What if we just, ignored it for now? I'll just scribble that out for now. What if we just ignored that? And we just looked at base times height. Now, if you're looking at this pyramid here, if it were just the base times height, base is basically area of base. So base, the area of base. So you're looking at the area of the base. If you calculate the area of the base, say for example for the square, if the area of the base is, if it's a 5, if you have a side length of 5 for this square base, that means the area of this base is going to be 25 because it's just 5 times 5. And a square has all equivalent sides, so it's going to be 5 by 5, length times width. So it's going to be 25 here. Now, if you just multiplied it by the height, and if we see that the height is going to be 3, if we multiply it by 3, we get a value of 75. So you're thinking, oh, 3 times 25, that's 75. That's the area of our pyramid. Well, that's actually way more than you think the area of the pyramid is. Because what's happening is you're taking this base and you're multiplying it by a consistent height. So what you're going to get is square stacked up on square. It's stacked up on square about 75 times. So you're stacking up this square 75 times on itself. And it technically has a height of 1. It's going to have a height of 1. When you're doing that, if you actually stack them up and do that sequentially, you're going to get a cube. So let me draw this cube out here. You're going to actually get a cube and not a pyramid. And you're thinking, oh wait, how is that possible? Well, how does this whole 1/3 come into play if it's going to equal a cube or a rectangular prism? No matter what I do, if it's a hexagon, it's just going to look like a hexagonal prism. It's not going to be a pyramid. Nothing unique to it. However, if you take that given figure, such as a cube here in this instance, and this works for any type of figure and any type of three-dimensional figure that you create, you can always make a pyramid out of that. What you're basically going to do is you're going to divide this by 3. So you're going to divide this. So you're going to do 3 times 25 is 75, base times height, and then you're going to divide it by 3 to get a value of 25. Now, what you're basically doing is, if you look at this pyramid here, and if you think about it closely, you can take this pyramid and take another pyramid on top. So if you look at this cube here, we're going to take a look at this given pyramid. This pyramid is actually going to be, this pyramid is only 1/3 of this cube. It's actually just 1/3 of this cube. So what you do is you basically stack together multiple pyramids, 2 other pyramids together, and it actually forms it actually forms this actual cube. It forms and represents the entire volume of this given cube. Now you can, make these different pyramids, and if you place them on top of each other in such a manner, you're going to create an entire cube. So if you put 3 of these together and arrange it in such a way, it's going to equal this cube here. So it's going to be 3 times. And this is just representative of a 2-dimensional view, so 2D view. And of course, that's going to create a square. You're given square by doing so. And you can always use geometric software to actually see. That's very complex to draw out, but that's the overall 2-dimensional overview so that you guys can understand that. So that's how you apply the volume of a pyramid formula to calculate its volume. Now let's look at the surface area of pyramids. So let's look at the slant height and surface area formula. So just as the altitude of a pyramid actually involves and correlates with the volume of a pyramid, it affects it, independent variable, affecting variable. What affects the surface area is actually going to be the slant height, a different part of a pyramid. So the slant height is the length of a lateral face's altitude. So remember, we saw those lateral edges. It's not your lateral edge, but if you look at one of the triangles, one of your lateral faces, all it's going to be is the height of that lateral face. Because we know it's an isosceles triangle, we now know that it's the height of that given triangle. And all the surface area is the total area on the figure. So all you're going to do is break it apart into separate sections in order to calculate the area. But I'll just be doing that for now, but I'll show you a shortcut in the next slide. So polygons of bases of pyramids have their own respective areas. So you're just going to calculate the area of your base of your pyramid. And then the lateral edges are always an infinite amount of triangles. So you're going to try and calculate the values of your area of the areas of your triangles. In this case, we're going to be looking at regular pyramids. So all you're going to do is calculate the area of one given lateral face or one of your isosceles triangles, and then multiply it by the amount of lateral faces that there are and add that to your base area. So if we look at this given pyramid here, and it's still a square pyramid. So if we're looking at this side length here, we're going to say that it's 4 here. So that means that the area of this base is going to be 16 units squared. So that's 16 units squared. And we're also given that our lateral height, let me just clear this out so we have some more space. Move this over here. So 16 units squared. We know that our lateral height, which is basically the height of this lateral face here, the height of this lateral face is going to be a straight line. Sorry, not a curvy line. So it's this height here. Let's assume that this height is going to be 4. Now that we know that this height is going to be 4, we know that the area of our base is going to be 16, we just need to calculate the areas of all of these lateral edges. So we know that our base equals 16 units squared. And our lateral faces, if you see here, we have a 4 here. That's our height for a triangle. Now, in order to calculate the area for a triangle, we need to know the base and the height. But we already know that one of the sides, the base edges, is going to be 4. And since it's a square, all base edges are equivalent. So your base here is going to be a 4. And now that you've discovered that it's a 4, all you do is multiply 4 by 4 to get 16, and then divide 16 by 2. So 4 times 4 equals 16 divided by 2 equals 8. And that equals our lateral face. And since we have 4 lateral faces, since we have 4 lateral faces, we're going to multiply that 8 by 4 since we know that all of them are going to be congruent. Since this is a regular pyramid and it's, of course, a square pyramid, so it's going to be 32 units squared. Oops. 32 units squared, and we're just going to add that to our 16 units squared. So 16 plus 32 equals 48 units squared. Very simple math, and computationally, it's a basic concept for surface area. You can do it straightforward, unlike you would do a volume formula, which is basically more complex. But now let's look at a shortcut formula for the surface area of a pyramid. So let's look at the net of a pyramid. And a net of a pyramid is basically when you take a pyramid and you're just going to tear it out and flatten it out completely. So you're going to pull apart the triangular pieces and you're going to flatten out completely so that it represents the total two-dimensional piece so that you can calculate the 2D area of the figure. And let's look at a different surface area outlook and develop our new formula. Now, this is a more of an enrichment part of this lesson, so please take notes because this will be very useful for you later on. So if we're looking at this net of a pyramid, so I'll just name this the net, and it's going to be square pyramid. If we're looking at the net of the square pyramid and say, for example, we're given our height here, one of our heights, intersecting at a 90-degree angle, and let's say that's 4. Let's say our base is also going to be 4, one of our squares here. So what the equation is, the new equation, shortcut equation is, it's going to be 1/2 LP plus B. And L is going to be representative of a lateral face. Sorry, lateral height. Lateral height. P is going to be the perimeter of base. And B is going to be the base area. Because we're calculating surface area here. So what I'm basically trying to convey here is, what we need to do is we have to figure out what the lateral height is. So, before we do that, we're going to try and figure out the area of this base. So know that we have a side length of 4, and we know this is a square pyramid, so the base is going to be square. So we have another 4 here, so it's going to be 4 times 4, which is 16. So great, we found out 16 units here. Now, what I'm trying to show you is a relationship between the lateral faces and the base. I want to take advantage of that to develop a shortcut in this equation. So now that we've calculated the area of the base, we can cross that out. So that's going to equal 16. Now, if we're looking at the perimeter of the base, well, if we already know the given side lengths of any figure given here, like a 4 here, we know that the perimeter of this entire triangle is just going to be 4 multiplied by 4, or 4 plus 4 plus 4 plus 4. So that means our perimeters are going to be 16. So we figure that out. Now we are going to calculate our lateral height here. We know the lateral height here, and it's going to be consistent for all equivalent isosceles triangles. So our lateral height is going to be 4. And we're going to multiply that by 1/2. Now, how did I come up with this equation? What I actually did, well, let's calculate this first. So we have 4 times 16, which is going to be your value of 64, and then 64, by 1/2 is going to be 32, and then 32 plus 16 is going to be 48, so that's going to equal 48. So the SA equals 48, surface area equals 48. Now, how I actually discovered this is, first you're going to calculate your base area. Very simple, you're just going to calculate the base area. There's not much of a shortcut you can develop there. What you can discover is, if you know how to calculate the base of the area, that means you have enough dimensions of your base to actually calculate the perimeter, which is the sum of all side lengths of your base. Now, once you've calculated the perimeter of your base, you're gonna add those together. So it's 16 in this case. But realize this: the base, all of these sides of your base is going to be the base of your isosceles triangles here. So if you've calculated all the sides of your bases, if you know those sides, they're going to be the bases of your isosceles triangles. So we know that the area formula for a triangle is base times height. So if you know the base of each and every single isosceles triangle, Well, what do you need to do now? So if you calculate the perimeter, you know the sum of all those bases. And then if you calculate the height, you can merely multiply it by the height to calculate for all of these isosceles triangles. And of course, divide by 1/2, because if you realize it, it's base times height divided by 1/2. So you're dividing the entire perimeter, which is the sum of all bases, multiplied by the height, which represents all of these isosceles triangles, divided by 1/2. So that's a bit of a shortcut here. I'll write it out here. So 1/2 LP plus B. All right, everyone. I hope you all enjoyed this video. I had a blast making this video, put a lot of effort into it. So I really hope that all of you guys enjoyed and took a lot away from this video. So please make sure to like and subscribe, and of course, turn on post notifications so you don't miss out a single upload. Visit our website at www.ecoreacademy.org. We've just finished it, final product of it. There we have full unlocked access to what we as an online educational platform actually offer for you. We have full unlocked access, as I said, to all of our integrated quizzes, worksheets, and note sheets that go along with each and every one of our videos, organized into their own separate lessons under organized course studies that you can access only by making a free account. So you can access it by making a free account, and of course get all of our perks there, such as progress bars, progress checks, quiz grading, all of that sweet stuff. We have our contact information available there, but of course you can email us at ecoreacademy@gmail.com. It's displayed on the screen. It'll also be down in the description below if you have any questions or if you just want to reach out to us. And please finally visit our socials in the description box below. We have their full links down there as well, so please check out the description after or before you watch all of our videos. And please visit our socials at Facebook, Twitter, and Instagram to see what kind of content we have there aside from our YouTube channel. And of course, check us a follow out there and use those mediums to share all of our videos. Once again, everyone, this has been the eCore Academy learning platform. And of course, this has been AJ Raj bringing you this geometry video. So once again, I hope you all enjoyed, and I will see you guys in the next one. Peace.